everyone to our Let's Talk to an Expert series, an exciting initiative by Xperimentor. At Xperimentor, we believe that science education should be engaging and evoke curiosity in children. Our goal is to inspire young minds through hands on inquiry based learning. In this series, we bring you talks by experts from various scientific fields. We believe the session will spark curiosity and provide a unique opportunity for children to engage with experts directly. Before we begin, we have few instructions for the session. The first is this session is designed by Mrs. Yamuna to be engaging, so please feel free to participate actively. To avoid audio disturbance, we request all of you to mute yourself during the session. If you have anything to ask or contribute, please use the raise your hand option. Yamuna ma'am will be asking questions throughout the session, so please use the chat box to drop your responses. If you have any questions, please post them in the chat box. We will try our best to address all the questions. The session will be recorded and shared on our social media handles. So today we are dabbling in the world of Math Magic Square, and we have an exciting guest with us. Joining us, Mrs. Yamuna Natraj, an engineer by education passionate about mathematics and chose to pursue teaching after a 7-year career at Infosys. Over the past 12 years, she has taught mathematics to primary, middle school, and high school children and also worked with various organizations. And her focus is on building a solid foundation paired with novel experiential approach through teaching or to teaching mathematics. We are excited to see you, ma'am, here. The floor is all yours.
Thank you, Aparna, for the wonderful introduction. Okay, so we are gathered here today to honor the birth anniversary of Srinivasa Ramanujan, a renowned mathematician. Since 2012, in India, we are celebrating December 22nd, the birth date of Ramanujan, as the National Mathematics Day. Even though he had no formal education in mathematics, the contributions he has, the significant contributions he has made in the field of mathematics, in mathematical analysis. He has done it in continued fractions, infinite series. Partition numbers are his famous thing. So in number theory, he has done a lot of contribution. And I just want to talk about Srinivasa Ramanujan today because it's in honor of him that we are having this talk. Since childhood, he has been good in mathematics. By the age of 12, he had completed learning trigonometry on his own by the book SL given to him by the undergraduate BSc students, and he taught them also about it. And by the age of 13, he had come up with many of his own discoveries as well. And by 14, I believe the school had a problem with the timetable, the number of teachers that were there and the students, they had to manage it. And he created the timetable for the school and gave it to them. And for that, he was given a prize as well. And by the age of 16, he was given a book by G.S. Carr called A Synopsis of Elementary Results in Pure and Applied Mathematics. And that was the book that Ramanujan carried with him. He went through it in detail and he came up with many of his results, which he noted down in the notebooks that he had. Though after his secondary education, when he went to the arts college, government arts college in Kumbakonam, he didn't pay, he was disinterested in other subjects. He didn't pay much attention to them. He just concentrated on mathematics. And as a result of that, he lost the scholarship. And even in degree college as well, even in mathematics, he chose to do questions only that which interested him in the exam as well. And therefore, he could not score much. And later on, he joined the Madras port as a clerk. Okay. And During his free time, he always carried that book by G.S. Carr, and he was making his own discoveries as well. He noted down all of that in three notebooks. Okay. And that was the one that he presented to G.H. Hardy as well. Like while he was working as a clerk in the Madras port, they recognized his genius and they connected him to different mathematicians. And then he started writing letters to the mathematicians abroad as well. And thus he got an invite by G.H. Hardy. Okay, so I'm sure all of you know about the story, but I just wanted to recap that, and I just wanted to bring in that in those three notebooks, the first notebook, the first chapter deals with magic square. So Ramanujan had created his own birth date magic square, and he had listed down many other formulae to create that, and many other interesting properties that he had noted down and all that. Even though it is for fun, the magic square is considered to be a recreational mathematics. So, but there are a lot of applications in discrete and combinatorial mathematics, as well as in graph theory, cryptography these days. Okay. So, and I thought this was a good introduction to start off with the magic squares. It's easy, and you also see the rigor that is required. The what do the mathematicians do? How do they find the patterns? So let's all have a look at that. Let me just present my screen. Visible to everyone, right?
Yes, ma'am.
Yes. Okay. So, okay. I just want to start at the beginning. The first ever written record of a magic square is from 462 BC. Okay. And the legend says that the river Luo, that is in China, was flooding. There was an annual flooding happening, and they tried appeasing the river god in many ways. But they gave gifts, they performed ceremonies, but nothing helped, and it had caused a disaster, havoc to them. So finally, once when the king is praying, he finds this turtle. You see some patterns on the shell here. Okay. So the shell, if you see, there are four dots there in the first one. If you write it, you'll have four there. And the next one has, if you count it, there are nine dots and two. And then there is three, five, and seven. And then we have eight, one, and six. And the king held this turtle in his hand. He saw this pattern. He observed that, he was told that all the rows and the columns and the diagonals as well, okay, the same thing here as well as here, they add up to the same sum, which is 15, as you can all see. Okay, you can take a minute to count if you would like to. Okay. And then they decided that they had to present the river with 15 gifts and then pray. So it is believed that after they did that, the river calmed down and life went back to normal. So it has a lot of significance. Like the magic squares are deep held in mysticism and the numerology, the feng shui, and all those places. It has a lot of significance. They believe that the magic square has some unusual powers in them. Okay, so let's see what is the mathematics of this magic square. Okay, can you all tell me if 2 cross 2 magic square is possible? When I say 2 cross 2, what do we mean? So we are saying that each row and each column and the diagonals should add up to the same number. But if I write AB here, in order for it to be the same, I would have to repeat that number here. Magic square, we generally don't repeat the numbers. We want it to be all unique and different, distinct from each other. Okay. So we say a distinct 2 cross 2 magic square is not possible. Uh, do anyone want to try and write a magic square which is different from the one that I showed in the previous page? You all want to try and see using the same digits 1 to 9. Can you make a magic square which is different from what is being shown over here? You want to take a minute to figure that out? Okay, since Deepthi, Rajiv, can you let me know if you want to try it out? Otherwise, we can move ahead. Okay, unable to do it. Fine. So let me just take you through that. So whenever we write, you see that even if you write this, the corner squares always have even numbers everywhere, and the middle ones have odd numbers. Okay, so when you rotate this, right, 816 on being rotated, this is being reflected here, and this is being rotated. The one down here is rotation. This one is rotation. Okay, and this is reflection. That is, the numbers are just being reflected over there on the other side. It's as though a mirror image of that is there. So all the other different ways that are possible are all somehow coming back to the same magic square. So there is only one unique magic square that can be created using the digits 1 to 9. Okay, so there is only one unique magic square that we get. And in math, like again, we look into why is the magic sum 15? Why should, so if you have, if you want to work on that, see, this is what you would have to do. Okay, so mathematicians look for all these. They want to see what is happening. Okay. So why should the central entry always be 5? Why cannot one go into the corner? What else can I do with this magic square? If I add the same number to each cell, would it still be a magic square? Would I if I subtract the same number from each cell, would it still be a magic square? What if I multiply, divide? What if I take the product? Will it still be a magic square? What if I take pairwise product? So when I say magic product over here, I'm talking about the product of each row being added together is the same as product of each column added together. Okay, so you can do a pairwise product. So mathematicians look for ways to generalize this. So once you know for a 3 cross 3, now can you do the same thing for a 4 cross 4, 5 cross 5? Can you predict what goes in the central cell? Is there a generic formula for an n cross n matrix or n cross n magic square in this case? I'm not going into the math work right now. So there are many different techniques to create the magic square as well. So if you are interested, let me know. We'll do it at the end. Right now, I just want to show you the beauty of these magic square and the mathematics behind it. Like what are the things that mathematicians are still looking for? What are they working on and all that? Okay, so there are different methods to create the magic square. I'm just skipping this for now. We'll come back to it later. I just wanted to show some interesting magic squares as well. So The first two on the left show the prime number magic square. It's a 3 cross 3 magic square with consecutive primes. And this is the smallest consecutive prime. It's a 10-digit long number. Okay. But for a 4 cross 4 with the consecutive primes, we are able to come up with smaller numbers. 5 cross 5, yes, even smaller numbers are possible. Okay, but for a 3 cross 3, you have to go till 10-digit prime numbers in order to come up with the consecutive primes being listed as in the form of a magic square. Okay, magic square need not always deal with numbers. So we have some interesting uh, patterns as well, the geometrical magic squares. This was a recent discovery. Like, I think in 2000s, they thought that, okay, since we have a formula to create the magic squares, for, you can give the number, any value to the numbers A, B, C, and get the magic square. So they created shapes. If you can see that, this is C, B, and A. So when I say C plus A, for C, A has been added to it, the shape. So you get different shapes over there. And when you combine all of them together, you'll get one shape which is the same either horizontally, vertically, or diagonally as well. I'll show you some interesting looking ones. Okay, I found them to be really amazing. But all these geometrical magic squares have been created only for 3 cross 3. Okay, so there is still scope. So whoever can create a higher order geometrical magic square, yes, your name will be written in history. Okay, so think about it. So very interesting magic squares, like just the same thing all over. Either you take it vertically, horizontally, or diagonally, you'll always get a hexagon. Some more interesting ones, not only some with spaces inside them, some with an arc. I just wanted to show some with an arc. Okay, that was something that I wanted to talk about. 3 cross 3 magic square. So whatever are the techniques for 3 cross 3 magic square, the same techniques holds true for 5 cross 5, 7 cross 7, 9 cross 7, basically all odd order magic square. So creating a even order magic square was difficult. They were trying to come up with a pattern, but recently, I think in 1900s, late 1990s, they have seen with the using the Excel sheet, they have come up with a formula to create a 4 cross 4 magic square as well, or all even ordered magic square as well. There's a beautiful pattern. So spend some time. See, the problem is very simple. Like, fill in all the squares, like get a 3 cross 3 or a 4 cross 4 or any higher order. All rows, all columns, and all diagonals should sum up to the same number. And that same number is called as the magical sum. And Ramanujan created a birth date magic square. His birth date is 22nd December 1887. Okay. So he took his birth date, he wrote them in separate columns. When you add them up, you'll get 22 plus 18 is 40 plus 87, 127 plus 12, 139. So the magic sum for Ramanujan's birth date magic square is 139. Okay. So the unique properties of the magic square that Ramanujan created is not only are the row-wise sum adding up to 139, the column and the main diagonals, but even the short diagonals, if you see, 10 plus 86 and 18 plus 25, the color-coded ones, if you add them up, it adds up to 139. Similarly, with these right slanting diagonals, short diagonals, 23, 16, 12, and 88, those also add up to the magic sum of 139. And 2 cross 2 in each of them again add up to the same magic sum. The color legend explains it actually better. 22, 87, 19, 11, all four corners, numbers from top and bottom, two numbers from left and right. The central four numbers adding up also gives up to the same magic number. Again, different legends are given over here. So let's see if we can create a magic square. I'll help you all learn to create a birth date magic square. So let's take today's number, today's date. Okay, today's date is, okay, let me write 27, 12, 20, 24. When you add them up, the magic sum, what would the magic sum be? Magic sum is 83. Correct me if I'm wrong, or let me know if you have any doubts. So we'll look into how to create our own birth date magic square. Okay. So now we saw that in Ramanujan's magic square, the four corner cells add up to the same magic constant, which is 83. So we already have 27 and 24 here. The middle two numbers are 20 plus 12, which is 32. Let's split that 32, okay, into these. You can take any number, okay. You can split it any which way you want. I'm splitting it up as 21 and 11. Basically, I'm making sure that the four corner cells also add up to 83, because I now have 27 and 24 on two corners. I wanted to ensure that the other two corners add up to the remaining two numbers that were there. 12 plus 20 was 32. So I split 32 as 21 and 11. Now, let's go to the diagonal. This principal diagonal, when I see 27 and 11 is there, the numbers over there also should add up to 83. So since 27 and we have taken 11, 20 plus 24 is 44, plus 1, 45. I need to split the number 45. Basically, we are partitioning the number 45 and writing the value in the remaining two cells over here. I want to fill the 45. It should add up to 45, right? So let's split it up and write 45 as 19 and 26. Okay. Now let's do the same thing for this diagonal as well. We already have 21 and 24. So what's remaining is 27 plus 12, which is 39, but we have taken 21 instead of 20. So it should be 38. These two cells should add up to 38. So we need to split in such a way that these two, anybody wants to give me a number that we want to split 38 as? Or shall I go ahead? Okay. Let me show you one. I'm writing it as 29 and 9. Now this makes it simpler. I just have to add up all the values over here and then fill in the remaining cell in that column. So 29 plus 19 is 48, plus 12 gives me 60. So I can fill in 23 over here. Similarly, over there, 20 plus 26 is 46, plus 9 is 55. 55 minus 83. So you can do the calculations. You'll get back 28 over here. But now, see the magic. When you add the last row as well, you should get back 83. 21 plus 23 is 44. 44 plus 11 is 55. And 55 plus 28 is 83. Okay. And now let's start filling in. We've also seen that each of these 2 cross 2 also should add up to the same magic sum of 83. So we already have 3 numbers filled in. So we can fill in the other number. Okay, such that all four of them together add up to 83. So the missing number here would be 25. Similarly, when I do for the bottom two squares, okay, 29 plus 21, 30, 50, 73. So we are left with 10 over here, 83. And let's complete this. You can now complete either taking a 2 cross 2, or you can take in the row any which way, because finally you should end up with a magic square. Okay, which satisfies all the properties that we saw in Ramanujan's magic square. Okay, this way you can create a, a birth date, or you can create a date magic square, any particular date of your wish. Okay, so you, be it your birth date, your anniversary, or any special day you want to highlight, you can create a magic square of that. And okay, so it's interesting. So the mathematics, the part of it is like Ramanujan created a formula also for that. So if you think of it, for those of you who understand algebra, the magic sum is nothing but a plus b plus c plus d. Right? So I'm just adding all the four values in those cells. So somehow I need to make sure that all these values in the column also add up to a plus b plus c plus d. So the way I can do it, if you see 25 here is 1 more than b. So I can just write, instead of a, I can say d plus 1. Right? This is d plus 1. And if you see over here, 10 is 2 less than b. So instead of that, we can say b minus 2. B minus 2. And this is c plus 1. C plus 1. And if you see that this column, when I add it up, the plus 1 and plus 1 becomes plus 2, and a minus 2 negates and goes off, and we are left with a plus b plus c plus d. Similarly, you can notice that, and you can fill it up. This is c minus 1. This will be b plus 3 or b minus 3. And this is a plus 3. So a plus 3 and a minus 3 and a plus 1 and a minus 1 cancels off, and we are left with A, B, C, and D. So you can complete the magic square, create your own formula, and you can use this to create a magic square similar to the one that we just saw that Ramanujan created for his birth date magic square, which has all these other unique properties. Not only the rows, columns, and the principal diagonals, we saw many other things that are like adding up to the same magic sum. Any questions so far?
Ma'am, Raghavendra sir
Hmm?
have jotted down something in the chat box. He asked that any date is in the same technique. Maybe.
Yes.
Okay.
Yes, it's the same technique. That's why I came up with the formula also. I just said that A, B, C, D you can use. You can
Right.
do the same thing. So it works for any date. Okay. So Ramanujan wrote this in his first notebook. And the first chapter, he has given the formula also for this.
So, ma'am,
Huh?
can the square have negative numbers also?
Okay. See, you can take up negative numbers as well, but we would prefer to work with natural numbers. Okay. In number theory, or mainly we work with natural numbers. You can create magic square with fractions, integers. Yes, everything is possible. Yes, I see that Rajiv has raised the hand. Can
Yeah,
I?
good evening. I have a question.
Yes.
So, is this possible only with a 4 by 4 matrix? Because in a 3 by 3, I think there will be only one unique combination, right?
Yes,
It's
yes. We saw
possibly,
that previously. I'm
yes.
not sure if you were there. So 3 cross
Yes,
3,
yes,
yes.
I observed.
Yeah. But here the 4 cross 4 is for birth date magic square, that specifically that I'm talking about, so that we can split the DD, MM and YY. We have split it up as like 1887 in this case. And in today's
Okay,
date, I took it as 2024. Okay.
got it.
So the birth
Okay,
date magic square is specifically for a 4 cross 4 magic square. This
4 cross
technique
4.
works for a 4 cross 4.
Understood. Thank you.
There are, for 3 cross 3 as well, there are like many ways to come up with. You don't have to start with 1 to 9 always. You can create your own magic square starting with any number. And then there are unique ways that you can see that always why do the central number have that value.
Sure.
Okay.
Thank you.
Thank you. Okay. Let me move ahead. If you've all seen this and if you want to create it, go ahead, come back to this, look into it, and you can create the form using this formula. Okay. The earliest 4 cross 4 magic square that is there is by this painting by Albrecht Dürer. Okay. He has encoded the year in which this magic square was created. It's here, 1514. I don't know if the numbers are not very clear, because if you see, melancholia generally represents sadness. There was a, I think, some natural calamity, I think earthquake or something, everything had gone. Okay, you can see a lot of stuff lying around, people are sad lying there. But the wall which contained the magic square was still standing. Okay, so I heard that, I'm not very sure, but I got to know that even today, this has a lot of like people believe that burying this magic square would make the structure stand without falling apart. So usually during the foundation, when they do the digging for the foundation of the house, the purohit generally writes something and digs it and places it near the foundation, it seems. And that is nothing but the magic square. So it's the magic squares are involved with lot of mysticism, and like they believe that it contains lot of power and all. So this is one such scenario in which it was depicted in the painting by Albert Dürer. And this is a church in Spain which has a magic square similar to the one that you see in here by Albert Dürer. But this, the magic sum is 34. And that is the, I think, the number of years Jesus Christ was alive. Okay. Is it 34 or 33, I guess? Okay, I'm sorry. I think it comes up to 33 and not 34. But the significance of why it's placed in the churches, that is the number of years that Jesus was alive.
But here the numbers are repeating, right, ma'am?
That's because they wanted to make it for a special thing. Okay. So that's the
Okay.
only place that, yes, they could not help it. And what they have done, if you see, is just been reversed. Now this magic sum adds up to 34. Okay. So they have taken the same thing. If you see the bottom row, it is 4, 15, 14, and 1. They've just reduced it by one of the numbers. Okay. And then this is 9, 6, 7, and 10. And now they have increased 1 over here, 11, and the rest of them stays there, such that the magic square properties, that is the number, the value in the each row and column and the diagonals add up to the same number, is retained. So they've just taken the above one and modified a little. 8, 11, 10, and I think 5 became 8, 10, 10. I know the values are repeating over here as well. 10, 10, 14, 14, and all that. But that's that was because of the significance that they wanted to keep it. The even order magic square is a little difficult to create. Uh, people had known about the techniques for odd order magic square long, long ago. Okay, but even order magic square only in the late 1990s, they discovered a pattern for an even magic square as well. But Benjamin Franklin, long ago, he had created this 8 cross 8 magic square. So then it was considered that even ordered magic square was considered to be very difficult to make. The magic square that he has created has these other properties as well. As the color legend shows, if you add up all these numbers as well, not only the rows, columns, and the main diagonals, whatever the color legend shows, if you add up those numbers as well, you get the same magic sum. So I just wanted to show you all the interesting magic squares, different magic squares that are available. And this is a night tour magic square. Like, there is an interesting problem in mathematics about Knight's tour. Like, given any square, like if you use the knight moves, will you be able to cover each and every cell in that square? Okay, so here there's an example of 6 cross 6 magic square. Okay, I start from here 1, take the knight's tour, go to 2 over here, 3, 4, 5. So if you complete, like, you'll be able to go to each cell once. Okay, you're visiting each cell in that 6 cross 6 square once. But when you add up all the numbers in the row and column, okay, so the surprising thing here was they all added up to 111. Okay, the rows and the columns, only the diagonals didn't. Diagonals were 92 and 134 or something, I believe. You can check for it. But all rows and columns added up to 111. So such magic squares are called semi-magic squares. That is, only the rows and columns are adding up to the magic sum and not the diagonals. So there are many kinds of magic squares. Okay, they have an inverse magic square, which is not a magic square at all. Many such things. Okay, we saw that a 3 cross 3 magic square has only one way to create the 3 cross 3 magic square using the digits 1 to 9, the first 9 digits. Okay, but for a 4 cross 4 magic square with the first 16 integers, there are 880 different ways. And for the 5 cross 5, the numbers grow large, and they counted this using computers. And from order 6 and all, they say it is just a statistical estimate. We can't know for sure because there are so many possibilities. Okay, just quickly, there are magic squares need not be always squares. Like, we can have magic triangles as well. Like, each side adds up to the same number. Over here, if you see, each of these add up to the same number. Similarly, if you go across, also add up to the same magic sum. Okay, magic hexagon. So you see a lot of examples over there. I can find it. Not only is it the magic square in 2D, we can create magic squares in 3D as well, such that each face of a cube or a tetrahedron, each face, when I check, it has the same, it adds up to the same magic sum. Okay, this has 11, 6, 7, and 2. So that's the reason it's been converted to this 2D structure. And then when you can convert that back into a cube or a octahedron. Similarly, a tetrahedron can be done from a square. So we can have 3D magic squares as well. Okay, there's been an open question in mathematics which has not been solved to this date in 2024. Okay, it's an open question. That is, it was posed in 1984, and Martin Gardner made it famous, saying that whoever comes up with the square of squares, a 3 cross 3 magic square. Okay, there are not only this $100, now there are many more prizes added to it. Okay, I've given links to all of this. Whoever is interested can let me know. We can send you the links. You can go check out. Okay, so And these magic squares, as I told you, have a lot of applications as well, and they have shown that it is equivalent to many of the higher mathematical uh, uh, properties that they have, like in congruent numbers, elliptic curves, and all that, which requires linear algebra, higher mathematics. Okay, so the one that Lee Sallows had created, okay, here the rows and columns and one diagonal, I think the right crossing diagonal adds up to the magic sum of this, but the other diagonal has a different magic sum. It failed. So till date, nobody has come up with this magic, like a magic square, which has a square numbers written in it, and it follows the properties of a magic square. That is, all rows, all columns, and diagonals adding up to the same magic sum. Euler created a square numbers for a 4x4 matrix. 5x5 matrix is also available. 6x6 matrix also, people have made the square number magic squares. But for a 3x3, till date, it has not been found. And it's one of the open question in mathematics. And I just wanted to go over the magic squares in Indian culture. We see this in as Lakshmi Yantra. This is nothing but the 3x3 magic square that we saw. Okay. So worshipped for wealth, fame, prosperity, and success. We have Kubera Yantra. If you see whatever the numbers written inside are these numbers. That's it. Because Kuber's lucky number is 72, so they have made up a magic square which adds up to that. We have Navagraha Yantram. So starting with Sun, if you see 618, this is the unique magic square that we have. After Sun, Surya, Chandra. For Chandra, what have we done? We have added 1 to the magic square of 1 to 9. Each cell, if you see, 6 became 7, 1 became 2, 8 became 9. 7 is 8, 5. So 1 has been added to each cell. And we have a new magic square for the Lord Moon, Chandra. And then comes Chandra, and this is Mangala. Mangala as in Mars. We are adding 2 to the magic square. So it goes 1, 2, Mangala, Buddha. Buddha is Mercury. You are adding 3 to that. Buddha, Guru, Shukra, right? Guru is here, Jupiter, Shukra, Shani is Saturn, and Rahu, Ketu. So this is how the magic square has been created. But because they believe in the power of that, there's a lot of, like, it holds a lot of significance. So there is a 4x4 magic square that you see in Rama Chakra, Sita Chakra, which is used to predict your future. So they place some values, like whichever grid it falls on, they say that, okay, they are able to predict the future. This is Shiva Shakti Yantra. There is Durga Bisa Yantra. This is the triangular ones that I was talking about. Not only about the square ones, there are triangular ones. You see a ring that people wear to ward off evil and all that. And even in India, since we are talking about the magic square that we have seen in India, at Palani, the 8th century, in 8th century, there is a pillar on which the magic square, the numbers have been etched in. Okay. And at Khajuraho, again, you see a magic square written over there. An 8x8 magic square at Gwalior Market Food Gate. Okay. So there are lots of instances that we have seen. So I know I didn't go into the details of the math behind it. So if you're interested, you can go ahead and figure out the formula for higher order magic squares. What would be the central cell entry for any odd order magic square? Birth date magic square, you can complete the formula. And we have given few more links that you can watch. Let us know. We can provide you these details. Okay. So I'll end my talk over here. If there are any questions, I'm ready to take them. You want to see the trick also? I had a magic card trick as well with respect to the magic square. So a card trick that you can do to create a magic square.
Rajiv sir says, sure, sir.
Okay. So, okay, I think what I'll do is I'll just log in from my other phone. Just give me a sec because I want to show it to you. I want to play it as an interactive game. Okay. So,
Ma'am, there's another question meanwhile that, one second. So Raghavendra sir asked if it is possible, can you share the links with me so that I can mail him as well?
sure.
Yeah.
I can send it over.
Yeah.
Okay. Uh, will you be able to mail it to them if I share it now?
Yes, ma'am. If you share it now, I'll mail it to them. No issues.
Okay. Or you want me to put it in the chat box over here?
Or that would be best. They can easily access it.
Okay. Let me just, yes, I'll get those. Is it possible to get all of them together? Or I think I should cancel. I just want to copy. How do I can put it up over here and let me stop sharing. These are very interesting things that I thought that everyone should see if they are interested in mathematics. Some of them talk about how they go about the different other important properties of magic square that I've not talked about over here. Mathematicians look for a lot of things in magic squares. So this is all related to mathematics. Few more, I'll just send it.
Ma'am, this is
Yes.
not related to this, but we have
Huh?
math clubs at our school. So could you please suggest any games over this things for the children for the science for the math exhibition or something where we can display any ideas or something, ma'am, regarding club?
Yes, lots can be done. Okay. So the demos that you can do, there are many things called proof without words. Okay.
Okay.
So it just talks about that. You can search for proof without words. Like for sum of first n integers, what is the formula for the first n integers, for the sum of first n square numbers, first n cube numbers? There are a lot more. Okay. Lots and lots you can do for like proof without words, as well
Proof
as some
without words is any website or what is that, ma'am?
you can search for that. Okay. Or you can write to us at Xperimentor and we'll get back to you with further details.
That would be great, ma'am. So if you can suggest for us exhibition, few
Yes.
ideas like it can be any interesting for the parents to come and small children will be doing it. It would
To
be really
interact,
great, ma'am. Yeah,
right?
yeah.
So,
Yeah.
and I know that there are many manipulatives also, manipulatives that you use. You can use those manipulatives and create few other things as well. So there are lots more. Okay, let me just quickly see if I can show you the magic trick, card trick that I wanted to do in the beginning, but then I thought I just left. Just give me a sec so that I can go on mute and reduce my volume here. Okay. Is it possible to allow me over there? Oh, I think I'm currently outside. I'm attending a math camp at Azim Premji University. So I'm not there at my usual place. So, okay, it's been visible, right? Okay, I just I want to flip the camera. Okay, why am I not able to do that?
Ma'am, is there an option inside the space where you can see yourself, or maybe down the below there's an option to do it?
Okay, I think I got it. Are you able to see this? Okay, I have drawn a 3x3. It's like a tic-tac-toe. Is it visible? If I
Uh,
draw using one hand, probably. I know it's going elsewhere, but can you see a 3x3 grid here now?
yes, ma'am, we can. It's a
Okay.
little blur, but yes, we can.
Yes, I'm so sorry about that. So let's play a game of tic-tac-toe. Okay. So I'll be
Maybe you should unpin the other window, ma'am. That way you can focus on the
I'm so
screen that you're trying to present will be, yeah.
I'll do that, sir.
Yeah, thank you.
Is it
This is
visible
better.
now? Yeah, okay.
Yes, it is. Thank you.
Okay. I want to be the first one to play the tic tac toe because I want to win. So I'll place it here. Let me know where do you want to go. I'll place your card open so that we play a game of tic tac toe. Okay. Where do you want to go? Can you write it in the chat, or if you can let me know? Like if I can probably name this A1, A2, A3. B1, B2, I've already placed it. This is B3, and this is C1, C2, and C3.
Ma'am, Rajiv sir says in A3.
Okay. A3, I'll keep it open. And now I'll place it at A2. Where do you want to go next?
C2, ma'am.
C2.
C2. I'll keep it this way. And then I want to go here. Where would you want to go?
A1.
A1. Okay. So I'll place it here. And where will you go next?
B3.
B3. And then there's no option. I have to go here. So finally, we ended up in a draw. You all played well and you got me to a draw. But that was not the main point for me. When I turn over my cards, okay, if you see, they all add up to the same magic sum. This is 8, 3, and 4, which adds up to 15. 1, 5, and 9 adds up to 15. 6, 7, and 2 adds up to 15. And even the columns. So we have come up with a 3 cross 3 magic square. Right? So now the interesting thing is, like, what was the order in which I had kept my cards so that I ended up showing a magic square to all of you. So you can think about that as well. So this would be a good activity as well for the kids to come up with and present it as the 5 is the first one. Yes, very nice. Because I want to play, because the central number had to be 5. Nothing else can go in there. That's the reason I chose to play first. I didn't want to let anybody else say where to place it. So 5 had to go at the central cellar as well. But then once I did that, what is the order in which I need to place the cards? So there's mathematics behind that. So you have to find the sequence in which you have to keep it such that you will get a magic square at the end. So this can be given as a task to the kids. They can figure it out and present it in the exhibition or demo that you want to do. Sounds good?
Yes, ma'am. Yes, interesting. Yeah.
Right. Yes. Anything else? Any other questions?
Do we have any questions?
Yeah.
So, ma'am, since we have no questions, but there are a few which we received during the registration time.
Mhm.
So, can we go with that as well?
Yes.
Okay, so
Uh,
I'll go with the first question.
Mhm.
So, the first question is, easy way to remember a multiplication tables.
Okay. So I would suggest that actually there is in Polypad, if you see, uh, there has been, there is a multiplication game that's been created. Basically, it's visual. You see 3 sets of 3 objects or 5 sets of 3 objects. You look at that and you see that it is 5 times 3 is 15. So you're able to associate as well as visually see why multiplication of 5 into 3 gives you 15 and not just learn it as a rote way. Okay, so I would suggest that's a good way to start. So it goes on in increasing order of difficulty as well. So in Mathigon, you can search for multiplication table. Okay, there's an app, there's a game that's really, really interesting, and I recommend it to all the young students to try it out.
Okay, thank you, ma'am. So we have another question, and it is asked that what is 0 to the power of 0?
Okay, that's not been defined, and I think you can search on it and you'll get to know why it's not been defined and as such. Okay, yes.
We'll move ahead with our third question, which is how to make students to feel mathematics easy.
Okay, so instead of giving them just the rules, I would suggest that show them why it works. Like instead of saying in fractions, for addition, you have to take LCM, do it this way. For multiplication, just multiply the numerator, multiply the denominator. And division, you just say that flip the other one. Why are you doing that? What's the reason behind that? Like give them instances wherein they see why are we doing that. Multiplication is, again, I always say represent it as a rectangle. So there are techniques in which instead of making children just learn the rules to work with it, they have to be given a chance to come up with the rule. So give them instances wherein they have to add half and 1/3 or half and 2/3. So how will they come up with that? So what is it that they can do? So they would have learned the equivalent fractions. So equivalent fraction, there are many manipulatives these days. Okay, the fraction tool that is available is really, really good to help with the equivalent fractions and from there getting to addition, subtraction, multiplication, and division as well. So I would suggest Basically for division, like I see by the time the students come to fourth or fifth, they would have to remember a lot of stuff. Okay. For fraction, you have to do it in a particular way. For decimals, you have to move the digits, like the decimal point, either to the right or to the left. They don't know why they are doing it. So give them a chance to learn or figure out how did mathematicians arrive at those rules. Okay, that will help them make feel that math is not just something that they need to remember, right? It's something, it's a lot more creative, and you can understand the thought process, the logical way in which it goes. That
Right.
should be it.
We have another fourth question, which is asked that how many symbols using whole maths. So I guess let me phrase it for you. So the person wanted to ask like how many symbols are used in whole mathematics. So do we
Okay.
have any numbers to it?
No, as in when you create something new, you can come up with your own symbol as well to give a placeholder to that particular thing. Okay, so they're infinite. Like you can come up with your own unique symbol as well once you create something.
Right. So we'll move ahead with another question, which is why one is neither composite nor prime. And there's a second part to this question as well,
Mhm.
which is why is there no Roman number for zero?
Okay,
So
okay.
I'll break it for you. The first is why one is neither composite nor zero. And then we can move ahead with the second part, like why
When
Roman
I
numbers do not
studied,
have. Yeah.
when I was in my school days, I was taught that one is a prime number. Okay. But then mathematicians found that considering one as a prime number caused many other things to go haywire. So they redefined the definition for the factors, or like the prime factors, the prime numbers. So prime numbers have exactly two factors. And if any number has more than two factors, it's called composite. One has only one factor, so it's neither being considered as prime because it does not have two factors, because now prime numbers have been defined. The definition for the prime numbers changed. It says the prime number should have exactly two factors. If any number has exactly two factors, then it's considered a prime. If it has greater than two factors, it is considered composite. Now, one has only one factor. So it's does not come under the category of prime nor composite. So that's the answer to that. And coming to the Roman numerals, why zero is not there? So accepting zero was a difficult thing. It took thousands and thousands of years for people to accept zero. Like you could imagine what we can do with one, two, three fractional numbers. Also, they were very comfortable with, but coming up with zero caused a lot of problems as well. That's the reason they didn't want to touch zero. Okay, basically you can't divide anything by zero. It goes, all the mathematics goes haywire. So mathematicians didn't want to touch zero, so many of them refused to accept this even as late as 1200s. Okay, but in India people were very comfortable with that. Aryabhatta had given the rules of how to use zero, what to do for each operation. So that's our contribution.
Okay. Ma'am, we have another question, which is how to make maths more interesting.
I think we already covered that. Like,
Yeah.
give them stories, let them know about why something came about, why some particular topic came about, who invented that. Give them the human aspect of it. It all came about because of a necessity. They wanted to express themselves. So, this is just a tool to express yourself. So, it involves a lot of creativity as well. So, I think the history of the mathematics has to be taught.
We have our last question from the
Mhm.
responses. So the question is activity to teach mathematics effectively. I think it is also very similar to, making maths more interesting.
Yes. So there are lots more manipulators these days. Okay, so you have your dine blocks. Like whoever wants can reach out to us at SciCraft Experimenter. We'll get back to you with the list of things that you can use to teach math effectively. The tools wherein children can play around with that, get a feel for why they are doing what they are doing.
Right.
Hmm.
Just do we have any other questions before we end up? I guess not. Also, you can mail us your questions on experimenter email ID, and then we can, revert back to it. So,
Thank you all.
yes.
Thank
Thank
you
you
so
for
much.
this wonderful session. This is my second session of yours. Once I
Okay,
attended that spirolateral, and that was very nice actually.
okay, thank
So looking forward for many more such interesting things. Thanks a
you. Yes,
lot, ma'am.
Thank you,
definitely.
ma'am, for making this session so interesting and engaging. I'm sure students and teachers had a wonderful time as well. And a big thank you for everyone to joining us today. We look forward seeing you again on 10th of January for our next exciting session. Registration links and further details will be shared with you shortly. Thanks again and have a great evening.
Thank you.
Thank you.
Thank you, ma'am. Bye-bye.